So for these next lot of examples, let's have a look. We're finding the inverse function, or if it's going to be a function, and then we can draw it up, and we have to draw the function. So we need to see whether we're going to have a function or not, or whether we need to restrict our domain. So the first one, y is equal to 8x cubed. Swap our x's and y's around. Manipulate. We get the cube root of x. Now, if we notice about the cube root of x, or firstly about the 8x cubed, what should we notice about this one? Well, if we found the derivative and we calculated it, then we could see that the first derivative of this would always be greater than or equal to 0. So it's only equal to 0 when x is equal to 0. So that means it's always increasing except at x is equal to 0, which means we don't have to do too much to the domain to worry about it being an inverse function. It will be a function. So there's our graph, and it's a little bit hard to see. If I can't zoom in on it at this point in time. But if we could, you'd see that you could get a bit more of a gap there. It does meet again at the 2 points where it meets y is equal to x, and that's why I put y is equal to x in this function as well. It also meets at the origin there, because when x is equal to 0, y is equal to 0. So it comes up and then turns in and goes back up. So it always increases there, so it's always increasing there. Notice we get that nice reflection at every point for the function, to get a function there. So log of x base 10, again getting our inverse. Y is equal to, swap the y and the x's, and we can get y is equal to 10 to the power of x. Now what we've got to do, what we have to do is remember that in this one, x is going to be restricted. So x has to be greater than 0, which means if we look at values here, so the domain there, and our range is going to be all y, so that's not a problem. So our domain for this one, well, that will become all x, because we swap with a or y, and the range would be, well, y is going to be greater than 0, and we know that because 10 to the power of x can't be equal to 0 or less than 0. So that works out nicely. Not a problem, as long as we just make sure we restrict our domain there, because we have to have a restriction because it's a log function. It shouldn't be too bad to be able to draw up both those functions. So there's y is equal to log of x base 10, and 10 to the power of x. We get that. Again, our nice reflections all the time. The critical points, obviously, where it's going to go through the axis there. X to the power of 5 minus 2. So again, x to the power of 5, if you found the first derivative, you'd see that's always increasing. X to the power is an odd function, so an odd power, so you know it's going to be always increasing. So again, we're going to have the situation where we don't have to worry about restricting our domain to get a function here. It's going to work out as an inverse function. It's without doing any manipulation. Critical point is only just where it's going to go through y is equal to x. How do you work that out? Well, put where that's going to be equal to x and start to solve it, if you can, easily. If you can't, then you can always do it through Newton's method. That's not a problem. If you learn Newton's method, you can find an approximation to any function there, so that's not too bad there. So you can start to solve that. Cube root of x plus 1, again, the cube root of, when we take the inverse and swap the values over, is an inverse which is then cubic. So again, not a problem with having to restrict the domain, because cube root will always keep rising, so will y is equal to x cubed. So you're able to solve it. Again, if you want to solve where it meets there, let x or y be equal to, because you're solving it, comparing it to y is equal to x, so you solve it at the same time. So again, if it's working out difficult to solve, use Newton's method. Log of x power plus 2 power of e. Again, all we've got to make sure is that because of this nature of the function, our domain's restricted already, so it shouldn't work out too bad. And remember, what's your domain and range there? We'll swap around there as well. So graphing that up, there's our function, the log function of x plus 2, and we've got e to the power of x minus 2. So that's e to the power of x and just shifted down 2 units. Notice they're crossing where it meets y is equal to x, so we make sure our graph looks like that. What we should take notice as well is in this situation, because we had a restriction in the function we start off with of the x-axis being an asymptote, Now the y value becomes the asymptote as well. So, sorry, it wasn't the x-axis, the y-axis before. It was this line, y is equal to x is equal to minus 2. So now that becomes y is equal to minus 2 as our asymptote. So the asymptotes swap around as well. Because the domains and ranges swap around, so do the asymptotes. So that's got to be considered as well. Same would have to go on here. We know that the domain of this one, all x, not a problem, but y is greater than or equal to 0. There's an asymptote on the x-axis. So that means for this function, the asymptote will become the y-axis. So when we graph it, there we go. Was an x-axis for y is equal to x plus 3, and that's going to keep going. It's going to eventually cut the axis when x is equal to 0, e to the power of 3. So which is a little bit more than 10, so it's going to be up here. So again, it will cut the axis there. I just haven't done my scale large enough. But now the y-axis becomes the asymptote for the log function. So the asymptotes will swap around as well. Y is equal to 1 of x minus 2. Again, this is where the idea of the asymptote comes in, because the domain of this function will be all real x, except what x can't be equal to 2. The range of the function was all y, but y is not equal to 0. So you can't put y is equal to 0 because 1 divided by anything gives 0. So again, the domain and range is going to swap around here, as you can see. The domain of this one will be that x can't be equal to 0, and thus, if that's the case, we can't get x is equal to 2. Y is equal to 2 because there's no way that can be 0, so you can't have y is equal to 2. So there's your asymptotes of your inverse function. Drawing it up gets a little bit messy. So the orange is 1 over x minus 2. So if you need to stop the video and have a look at this carefully, then feel free to do that. But there's our asymptote of x is equal to 2. So when we go to the pink, y is equal to 2 becomes the asymptote for our new function. So hopefully you can see that that's going through 2 there. That was going through 2 there. So our asymptotes swap around. They meet at y is equal to x. And you can see the function there and how it's flipping with, and in line y is equal to x with the line here. And the same over this side. So you can start to see that they're starting to mirror each other. Those two parts, those two parts. So again, being able to draw it, you need to be able to do that reflection. Sometimes it's not as easy as it might seem. And 8 here, we've got a situation where we've got an exponential function, and obviously that's going to become a log function. It's a little bit more complicated than this log function. But again, what's the domain and range? Domain, x is going to be anything, y is greater than 0. So that's we have to consider that. Greater than 0 there. So again, x would be greater than 0, and y is going to be, and x is going to be greater than 0, and y can be basically any value, so it won't be a problem. We're able to draw our function, draw our asymptotes. Again, where does it meet up? Well, again, we can set y is equal to x and solve it with that function and be able to solve it there. Again, probably going to have to use Newton's method to find that value if you're going to get it exactly. So that would be that's the only real challenge there. But again, as long as we're drawing it and we can show that they meet up at the same point on y is equal to x, and that will make sure we've got an idea of what exactly an inverse function is, what its graph looks like, and what the relationship with y is equal to x.